Alright guys, so in this video, I'm going to show you how to explain the hybridization process for OCN minus. Okay, so as usual, first thing first, we have to calculate the total number of valence electron. So for oxygen, 6 valence electron times with 1 oxygen atom. Carbon, 4 valence electron times with 1 carbon. Nitrogen, 5 valence electron times with 1 nitrogen atom. And also don't forget we have the negative 1 charge here. So for the negative charge, so we need to add 1 electron. So the total number of electrons that we have here is 16. Then draw the Lewis structure. Okay, since carbon is the least electronegative atom, so carbon will become our central atom. So draw the skeletal form. So we already used the 4 electron. So 16 minus 4 is equal to 12. So the 12 electron, we need to make sure that our surrounding atom is octet first. Alright, so we already used all the electrons. So no lone pairs on the central atom. And then check our Lewis structure. So we have carbon as our central atom. So we need to make sure that carbon have 8 electrons. So now we only got 4 electrons. So we need to make a multiple bond by using any lone pairs on the surrounding atoms. So this is the best Lewis structure for OCN minus because the formal charge is the lowest, which is closest to 0, and also the negatively charged is on more electronegative atom, which is oxygen. Next, determine the electron group for carbon and nitrogen. So remember, we need to explain the hybridization process of the central atom and also the surrounding atom that got multiple bonds. So for carbon, we have 2 bonding pairs, so 2 electron group. Nitrogen, we have 1 bonding pairs and 1 lone pair, so again 2 electron group. The electron group arrangement for 2 electron group is linear, and the type of hybridization is sp. Then draw the valence electron orbital diagram of carbon, nitrogen, and O- at ground state. So for carbon, we have 2s2 and 2p2. Nitrogen, 2s2, 2p3. For O-, remember, we need to put it as O- because the formal charge is negative 1. So for the O-, we need to add 1 electron. So it will become 2s2 and 2p5. At excited state or promotion of electron, for carbon, have a look at the Lewis structure again. For single bond, we have sigma bond. For the multiple bond, we have 1 sigma and 2 pi bond. So for carbon, we need 4 single electron. At ground state here, we have only 2 single bond. So we need to promote one of the electron from the 2s orbital into 2p. So at excited state, now we have 4 single electron. For nitrogen, have a look at the nitrogen here. We have 1 sigma bond and 2 pi bond. So we need 3 single electron. So at the ground state, we already have 3 single electron. So no need to promote the electron. For the hybridization state, so we know that we have sp type of hybridization. So since we have 2 electron group, we are going to mix only 2 orbitals. So for carbon, the hybridization state is sp hybrid orbital. Another 2 orbitals here, we are going to label it as 2p unhybrid orbital. For nitrogen, also sp hybridization. So mix the 2 orbitals, we will get sp hybrid orbital. Another 2 orbitals, it will become 2p unhybrid orbital. So for the single electron in hybrid orbitals, will produce a sigma bond, while in unhybrid orbitals, if we have single electron, it will produce the pi bond. So let's check back our Lewis structure. For carbon, we are going to have 2 sigma bond and 2 pi bond. For nitrogen, we have 1 sigma bond and 2 pi bond. Next, we are going to draw the orbital overlap. For carbon here, the sp hybrid orbitals, the electron group arrangement is linear. So we are going to draw the linear shape. This one is for carbon, sp hybrid orbital and sp hybrid orbital, where each sp hybrid orbitals got 1 single electron. And then for the nitrogen, we know that the 1 sigma bond here comes from the overlapping of the sp hybrid orbital of nitrogen with one of the sp hybrid orbitals of carbon. Okay, so the sp hybrid orbital for nitrogen also have linear shape. Label the sp hybrid orbital. This one is for nitrogen, and then don't forget to put the electron. The overlapping of these 2 sp hybrid orbitals end to end will produce a sigma bond, and also another sp hybrid orbitals here we have a lone pair, and then another sigma bond here is from the overlapping of the sp hybrid orbitals of carbon with 2p orbitals of O minus. So remember, the 2p orbitals got a dumbbell shape. So draw the dumbbell. So the dumbbell here is for O minus. Label it as 2p. So this is the electron from O minus. The overlapping end to end will produce a sigma bond. Next, we have 2 unhybrid 2p orbitals of carbon and 2 unhybrid orbitals of nitrogen. So these 2 unhybrid orbitals will produce a pi bond. So the formation of pi bond is by overlapping of the orbitals sideways. So draw 1 2p of carbon and 1 2p of nitrogen. So we are going to label it as 2px. So this one got 1 electron and this one got another electron. The sideways overlapping produce a pi bond. And then we have another 2p unhybrid of carbon overlap with another 2p unhybrid of nitrogen. So this one is 2px. So we put this one as 2py. So now we have 2 sigma bond and 2 pi bond for carbon, 1 sigma bond and 2 pi bond for nitrogen. So now let's explain the formation of sigma and pi bond in OCN minus. So the formation of sigma bond, so we have 2 sigma bond here, right? So for the orbitals O minus, okay, we have 2p orbitals of O minus overlap with sp hybrid orbital of carbon, and another sigma bond is from overlapping of sp hybrid orbitals of carbon with sp hybrid orbitals of nitrogen. Since this one is the formation of sigma bond, so the overlapping is n to n. For the formation of pi bond, so we have 2 pi bond here. The formation of pi bond is by overlapping the 2px unhybrid orbitals of carbon with 2px of unhybrid orbitals of nitrogen, and another one, the 2py unhybrid orbitals of carbon with 2py unhybrid orbitals of nitrogen sideways or side by side. That's all for the overlapping of orbitals and the hybridization process for OCN minus.